Welcome to Titration in pH Part 2. I want to begin by reviewing a strong acid, strong base titration. So for my strong acid, I'll use hydrochloric, and my strong base, sodium hydroxide. The result, table salt and water. Here's where they would be placed in our titration apparatus: sodium hydroxide in the Bure, and down below in the Erlenmeyer flask, the hydrochloric acid. For simplicity in all of these slides, I'm going to use the 0.1 molar solution of each. Let's take a look at what the titration curve looks like, and this we've covered before. We start off with a fairly low pH, assuming that 100% of the HCl dissociates, and if it's 0.1 molar, which is 10 to the minus 1, it would give us a pH of 1. As we proceed and add our NaOH, we'll eventually reach a point in time where half of the HCl has been neutralized, and we'll essentially have a solution which contains HCl and the sodium chloride it produces. At the equivalence point, we have only the table salt present. We have equal moles of the acid and the base that have essentially neutralized each other, and all we have is a salty solution. Now, we learned in a previous program from the pH of salts that sodium chloride comes from very strong acid and strong base, both parents being very strong. As a result, the ability of the sodium ion and the chloride ion to react with water is negligible. Hence, they have no effect on the pH. And we have a pH of 7 at this point. As we continue on with our titration, we essentially now have excess sodium hydroxide, and we'll finish with a fairly high pH, approaching 13. Now we're going to look at various combinations of strong and weak acids or bases. So let's start with a weak acid, and the weak acid that I'll use in this case is ethanoic acid with a strong base. So this would be our reaction. Again, I'm putting the strong base up above and my weak acid down below in the Erlenmeyer flask. Here's what the pH curve looks like. I'll highlight a few of the differences. First off, being a weak acid, our ethanoic acid only partially dissociates, so a 0.1 molar solution will have an elevated pH, perhaps somewhere around 3. As we proceed with our titration, the sodium hydroxide is going to convert the ethanoic acid into sodium ethanoate. It happens to be the conjugate salt of our weak acid. This constitutes what we call a buffer solution, where we have a weak acid or a weak base and its conjugate present, and they're present in this region of the graph. We'll learn more about buffer solutions in a later program. If we reach a point halfway to the equivalence point, there's an interesting feature that occurs, that if we look at the intersection of our curve and the pH axis, we'll see that we can determine the pKa of our weak acid, ethanoic acid. At point 3, we've essentially neutralized all of our acid or base, and all we have is a salty solution containing our sodium ethanoate. Now in this case, this salt happens to be slightly basic in nature. That's because it comes from a weak acid, and the sodium portion of our salt comes from a strong base. Hence the ethanoate ion is capable of altering our pH, as we saw in an earlier program. And finally, we have excess basic salt and excess strong base present in region 4, leading to our elevated pH of around 13. Let's look at a different combination, this time putting the weak base at the bottom and the strong acid up above. Here's the typical curve now. Let's look at where we start. With only the base present down below and being a weak base, we're going to start with a pH of somewhere around 10 or 11. It won't be as high as 13. If it was sodium hydroxide, it would be. But in our case, being a weak base, it only partially ionizes the water. As we proceed to add our HCl, we start to produce the conjugate salt. This then results in the formation of our buffer solution, as we would have both ammonia and ammonium chloride present in this region. Eventually, we'll reach a point where we have the equivalence point. We have equal moles of acid or base. And as before, neither the ammonia or the HCl are present. Our dominant species is the ammonium chloride. Ammonium, coming from a weak base, is a somewhat weak acid, and we would reach this equivalent point in the acidic region, somewhere below 7. I'd like to note though at the halfway point, we have a little bit of a trick we can use to determine the pKb of our base, ammonia in this case, by reading across and determining the pH. From that we can determine the pOH and hence the pKb of our weak acid. Again at 3, all we have present is our ammonium chloride, and that is going to be a somewhat acidic salt, giving us a pH at the equivalence point in the region below 7. And finally, in our last region, we have only the acidic salt and our excess strong acid, so we'll approach a pH of 1. Now let's look at the titration of a strong acid by a weak base. So I put my strong acid down below, the hydrochloric acid, and the weak base up above in the burette. So I start off much as we did before with a strong acid. Being a strong acid, it completely dissociates. We start with a very low pH of about 1. When we reach our equivalence point, we're going to have present the ammonium chloride. The ammonium chloride is a slightly acidic salt. That salt will then result in a neutral pH of less than 7. As we move further beyond, we're now going to have a solution which has our excess ammonia and ammonium chloride. That's a situation with the weak bases and its conjugate salt. So this would be designated as our buffer region. And eventually we'll reach a point later on where our dominant species is now really the excess weak base affecting our pH. Our final combination is a weak acid and a weak base. So again, my examples, the ethanoic acid and ammonia. And here they are placed in the containers. So a few points to highlight here. Again, we're going to start at a pH of about 3 because we have a weak acid present that only partially dissociates. Our equivalence point's a bit messy. I'm showing it here, it could be 7, but it could exist over a fairly wide range because we have a fairly complicated system where we have multiple species present due to the multiple equilibria and their individual Kas and Kbs. So we don't get that sharp drop-off that we see in all the other curves. And finally, we'll finish in a pH in the basic region as we have excess weak base. So as a quick recap, what one needs to be able to do is to interpret the various graphs. And what I mean by interpretation is you need to know, first of all, where you're starting and the intercept with the pH acid. It needs to reflect the idea whether it's strong or weak. You need to be able to determine the pH at the equivalence point and whether or not the salt that's produced is going to modify that pH from 7. You need to know where the buffer regions are, places where you have a weak acid or weak base and its conjugate. Finally, you should know a couple of tricks to determine the pKa and the pKb at the points halfway to the equivalence point.